Okay, so we're gonna solve this. This is a Zener regulator circuit. So what's going on here is that we're using this Zener diode. In reverse bias, you can see that the negative is connected to the anode of the Zener. And Zener diodes are engineered to break down at a particular voltage. In this case, our Zener voltage, our breakdown voltage, is 8 volts. Because it's in parallel with our load, this would be considered our load resistor, there's going to be 8 volts automatically at that load resistor. And so Zener diodes can be used to regulate the voltage on a particular load. So if you had a load that could only handle 8 volts, but you only had a source of 15, you could throw a Zener diode in parallel with it to make sure that it is going to stay at that 8 volts. As we learned about in learning task 3 of module A6, there's a few things you're looking for in a Zener regulator circuit. One being that the Zener voltage is going to be less than your source voltage. That has to be true if it's going to work, if it's going to regulate. As well as you need a resistor in series. So this is called our RS, either our series resistor or shunt resistor. It's going to actually act as a current limiting resistor to limit the amount of current going through our Zener diode. Zener diodes they can only handle a certain amount of current. They're given a wattage rating, so you cannot exceed that wattage rating. So if the current multiplied by the 8 volts is going to exceed the wattage rating, then that Zener diode is going to burn up and potentially explode. So that's why you got this resistor in series here. So a question might be posed to you: what is the current in this particular circuit going through the Zener diode? So what is the current through the Zener? So like any sort of electronic circuit, we're gonna probably use our Ohm's law, and we're gonna use our Kirchhoff's voltage and current laws to solve this equation. So we've already determined that we got the 8 volts across our load resistor because it happens to be in parallel with our Zener diode. So they share the same potential difference. And you can see that like this point here is common to that branch and the Zener branch, as well as this point here. So they must share the same potential difference or same voltage. That means Kirchhoff's voltage law states that all the voltage drops need to equal the voltage rise, where our voltage rise here is 15 volts. If we have used up 8 volts over here, then the remainder of that voltage needs to be used up across this resistor here. So we must have the difference between 8 volts and 15 volts, which is 7 volts, across this resistor here. So that's going to leave us with 7 volts. All right, so now, because we know two values, we can take the 7 divided by 250, and that's going to give us our current using, of course, Ohm's law, I equals V over R, of 28 milliamps. going through our shunt resistor or our series resistor. Okay, and we have two values here. We got resistance and voltage, so same thing. We're going to use current or Ohm's law. I equals V over R, 8 over 300, which is going to give us it's going to give us 26.6 repeating milliamps. Okay, now we're going to use, just going to clear a few things up here. Again, we're looking for the current going through our Zener. So now we're going to use Kirchhoff's current law. If we have 28 milliamps flowing through here, it's going to come to this junction, this node. Now it branches off. You got 26.6 going through our load. Well, there must be the difference of that 28 and 26.6 going through our Zener. So the current going into a junction must equal the current coming out of that junction. So 26.6, take 28 minus 26.66, gives us 1.3 repeating milliamps going through our Zener diode. And that's how you go about solving that particular question.